The purpose of today's lesson is to show representations of a linear pattern. Now they're referencing the previous lesson, but we didn't go over that. But if you want to look back at that, feel free. Okay? What we're going to do is, these are blocks, and we're going to compare what happens from stage 1 to stage 2 to stage 3. And we're going to see that it's a linear pattern. It forms a line. Okay? How many new blocks are added to the pattern from one stage to the next? Okay, well, let's consider here. We've got 3 blocks, right? Yes. All right, and so we have 3 here, and then this next one we have 3. Well, how many are added to those 3? Looks like we have 1 and we have 2. So 2 blocks are added to this one. Then let's see, on this next one we had 5, so we have here to here. How many blocks are added to this one? Well, looks like the same thing. Each time 2 are being added. So how many blocks are added to the pattern from one stage to the next? The answer would be there are 2 added. So we're going to complete this table over here. In stage 1, the number of blocks we have is 3. Stage 2 is 5. Stage 3 is 7. What do you think? Right. 9 and then 11. So what's happening each time? Okay, where did it go? I'm going to pause it and get back to it. Okay, I'm back. Sometimes it just jumps around. Alright, so the difference between these two, obviously, is 2. 2, 2, and of course 2. This column is called the difference column. You're going to hear that for the rest of your linear career. This is the difference column. These are also the rate of change, okay? Show where you see the rate of change in your column. Well, it's in this column. It's the rate of change in the Y column, or the right half of the column. Rate of change. All right. Create a graph of this data. Where do you see the rate of change on your graph? Okay, so let's go 2, 4, 6, 8, 10, and same over here. Let's do that. 2, 4, 6, 8, 10. Alright, and then let's graph these points. At 1, it was 3. So 1, 3. And at 0 stage, how many did we have? What do you think the first stage would have been? Ah, yes, it would have started with a 1. Okay. At stage 2, we had 5. Get that there. And at stage, I'm going to jump all the way to 4 is 9. And then you get the idea here. And 5 is 11. Okay. So those are our points. We're going to put that one in there, just be consistent. But what we want to do is we want to notice what the rate of change is here on this graph. So I like to always think of it as rise over run. Rise over run, rise over run. So what is happening each time? Each time we're going up 2 and we're going over 1. 2, 1. So up 2, over 1. So notice we can find the rate of change on the graph. The rate of change. And I'm going to use this symbol. That symbol is change. That's what they use in science also. That's a symbol for change. Rate of change is 2 over 1, also known as 2. Okay, so this next part is somewhat challenging. What is the simplified form of the equation that gives the number of blocks T for any stage S? Where do you see the different pieces of the equation in the geometric model, table, and graph? Okay, so what we're trying to figure out is, think back at some previous equations. We did y equals 2x, y equals 3 halves x. Remember we did those examples? Well, it's similar here, but now instead of the y, it's being replaced with a t. Okay, so we're going to have t, and our rate of change, remember, this is your rate of change, this number in front of the x, but we're using an s in this example. What was our rate of change in the graph and up here in the table? It was 2. Exactly. So far we have t equals 2s. Sometimes we had a number on added or subtracted at the end. Well, what is that? That would be where it crosses the table or the graph at the y-intercept. So what is this number right here? That's what goes in here. It's a positive 1. So anytime you see a line on a graph, this number is going to be the number that's added or subtracted. Okay? And if you thought back up here, we went back to the table, and we went down to 0. Well, if we went back 1, we would have to go back 2, and that would end up at 1. So this is another way we can find the number that you add or subtract on the end of the equation. Okay? Alright, our next question is, the pattern above is a linear pattern. Describe how a linear pattern grows. Describe what the graph of a linear pattern looks like. Well, there's many different answers, but some of the information, I'm going to write above because I'm limited with space, is it has a constant rate of change. That is a linear pattern. It also, with the graph is a line. That is linear pattern. And then we have our difference column on the table. So these are some examples of a linear pattern. Sorry. Alright, let's look at this next lesson. It's very similar to the previous one. It helps if you highlight. So let's see if you can't figure out how to get the table. So pause it and come up with the table on your own, please. Okay, did you get the same thing I did? Notice my nice highlights to show each time 3 is being added. So what is that? That's our rate of change. And that's also what is in the difference column. This is our difference column, the right side. But notice this first side over here, each one of these is adding 1. Okay, keep that in mind. Create a graph of this data. So go ahead and graph those points just like we did previously. Alright, did you get the same thing I got? Plotted the points, and I used my highlighter to find the rate of change. So how much did I go up and over, and should have gotten 3. Okay, now we have to come up with an equation. So we know it's going to be t equals something s plus or minus something. Remember we talked about this number in front is our rate of change. Well, we know what that is. The rate of change, this is an s, is what? 3. So, oh boy. So we can put that right here. Alright, that's your rate of change. This number is the y-intercept. Where does it cross? If we were to draw this line, where is it going to cross? The y-axis. Oh boy, it's somewhere down here. Well, this number is 0. So what can you make an educated guess about? Yes, that it's going to be a negative number because it's going to be below 0. Well, could we just kind of go backwards and go over 1 and then go down 1, 2, 3? Could we do that? Yes, we can. That's one way to find it. So the pattern is, we normally go up 3 over 1, but now we have to go down 3 over 1. So let's go down 3, right here, down 3 over 1, and where did you end up? At a negative 2. Exactly. This is the y-intercept on the graph. So that's one way to find it. The other way would be to use the table and go backwards until you get to 0. Okay? Is this pattern a linear pattern? Sure it is. Yeah. Let's list why. Well, with the geomodels, what is happening? Same number of blocks added each time. Same number of blocks added each time. Added each, it looks like teach, but this is an addition sign. Added each time. Alright, what about the table? First column, or the second column, it has the same difference, so each time the number is changing by the same. And then lastly, the graph, it forms a line. So that means it's linear. Those are the stipulations, or the requirements for a linear representation. Okay, describe what you see in each of the geometric representations of a linear pattern. Make connections between the different representations. So I kind of just gave you some hints on the previous one. In order to be a linear representation, or a linear pattern, a linear pattern, what's a requirement for a geometric model? What's a requirement for a table? What's the requirement for a graph, and then for the equation? You give me in words what is a good explanation as to why a geometric model would be a linear pattern. So this is due tomorrow. Due tomorrow. When the sun will come out tomorrow. Alright, this concludes our lesson on representations of a linear pattern.